Hello. In this video, we'll take a look at a Verilog model for the single cycle RISC-V processor, and also take a look at the test bench to prove that it's correct. So here's the design of our overall system. We're going to have a RISC processor comprising the data path and controller, just like we talked about. We also need the memories, and let's pull these memories out of the data path because typically they're external to the processor core. So we'll have an instruction memory and a data memory. The data path will send the program counter to the instruction memory to say which instruction to fetch, and it will get back the instruction from the RD port of the instruction memory. That instruction will go to both the data path and the controller. To access data memory, the data path will take the ALU result signal, send it out as data address to the address port of the data memory. We'll send the write data value to the write data port of the data memory, and it will get back the read data signal from the read data port of the memory. And there'll be a write enable signal for the data memory called memwrite, just like we already have from the controller. The controller will receive the instruction, and based on that, produce a bunch of control signals. The data path will reply with the 0 signal when the answer is 0. And the data path and controller, both data path anyway, receives a clock signal and a reset to initialize the program counter to the beginning and execute instructions one at a time. Let's switch over now to the test bench. So this processor is going to run a program to tell us if it's correct. And there are a couple strategies for testing a processor. One is something systematic that applies a whole bunch of tests to check each kind of instruction individually. Another is a more holistic but ad hoc testing methodology where we put in a program that exercises all the programs, all the instructions, and then we check the program produces the right answer in the end. So for this simple processor, we're going to do this ad hoc technique of a program. So let's walk through the program and see what should be happening. We start main. We're going to add I, x2 gets x0 plus 5. Remember, x0 is the 0 register. So this should put the value 5 into x2. And this instruction, let's say, begins at location 0. And this should say writes the value 71 into address 84 when we're successful. All right, so at address 0 instruction memory, we have our first add I, and x2 gets 5. Next instruction, next add I, makes x3 get 12. And the next add I makes x7 get x3 minus 9, which should be 3. So this is testing addition of negative numbers. Then let's test the OR instruction. Well, OR x4 gets x7 or x2. x7 was 3. x2 was 5. So 3 or 5 in binary. 3 is 0, 0, 1, 1. 5 is 0, 1, 0, 1. So the answer should be 0, 1, 1, 1, which is 7. Now let's test the AND instruction. So AND x5 gets x3 and x4. x3 was 12. x4 is 7. 12 is 1, 1, 0, 0. 7 is 0, 1, 1, 1. Or AND those together, we get 0, 1, 0, 0, which is 4 in decimal. Next, let's do an add. We add x5 gets x5 plus x4. x5 had been 4 from the AND. x4 had been 7 from the OR. So when we add them together, we should get 11. Then we'll do a BEQ, x5, x7, AND. So x5 was 11, x7 was 3, so they're not equal, so this branch should not be taken. So we test that not taken branches work. We continue and test the set less than instruction. We'll see is x4 less than x3. So is x3 less than x4? x3 was 12, x4 was 7. So is 12 less than 7? No. So the answer on set less than should be 0, false. So now x4 is 0. Next, we'll do a branch on equal. Is x4 equal to 0? It is, so that should be taken. So we should skip over this add I instruction. This add I would put a 0 into x5 if it were executed, which would mess up the contents of x5. So now we're up here at address 28 in instruction memory. We do another set less than. Is 3 less than 5? Yes, it is. So set less than should produce a 1. This way we're testing both set less than producing a 0 and a 1. Then we do an add. x7 gets x4 plus x5. x4 was the 1 from the set less than. x5 was the 11 from up here. So when we add them together, x7 should be 12. Then subtract x7 gets x7 minus x2. That's 12 minus 5 should be 7. And we'll store that value of x7 into location 68 parentheses x3. So x3 contained 12. 68 plus 12 is 80. So we should store the value 7 into memory location 80. We're testing that we can write to memory. Now let's test that we can read the value back. So we'll load from address 80 relative to x0. That's also address 80 since x0 contains 0. And we'll load that into x2. So now x2 should have the 7. Let's test a jump and link instruction. So we'll jump to the end. That way we're seeing that we can step over this instruction that would be messing up x2. Now let's do an add. The jump and link should put the return address, which was hexadecimal 40 or decimal 64, should put that into the x3 register. So let's check that it's there by doing an add. x2 gets x2 plus x3. x2 was 7. The link value was 64. So added together, we get 71. And finally, let's store the 71 into memory location 84. So at the end of the program, we should see a write, a memory write, of the value 71 into the address of 84. And if any of the instructions messed up along the way, if we had any bugs in the processor, then it would be unlikely that this would still come out correct and we'd get a wrong write. So next we need to translate that RISC-V program into machine language. And that's kind of a tedious process. It's best to do it with an assembler. And here we get the 18 different machine language instructions corresponding to those 18 instructions of assembly language.